In this unit, we're going to continue our study of definite integrals, and we're going to conclude with the fundamental theorem of calculus, which is going to tie all the work we did with derivatives back to the work we're doing now with integration. As a stepping stone towards that objective, we're going to look at why we would want to do these integration calculations in the first place. We've already done some with velocity and distance, but it's worth knowing that that general relationship, that where we know the rate of change through some kind of measurement device, and we want to know how much change has occurred in total over some time interval, that general question is always going to be answerable using integration. If our rate of change is velocity and we want to know how far we've traveled, distance, then the net change will be the integral of velocity. A similar example is given here. Suppose we have water flowing into or out of a tank at a rate, key thing here, of 200 minus 10t liters per minute. Positive values here indicate that the flow is into the tank, so positive is into. How could we write an integral that expresses the change in the volume of water in the tank during the first 30 minutes of filling? Well, this is like adding up how much distance did we travel if we know the velocity. What we're going to want is the integral of the flow rate, and that's going to be dt, and it's going to be from t equals 0. Our units here are minutes, so it'd be t equals 0 to 30. And the parallel we should be thinking about here is if we have r of t, and we think of the units, liters per minute, times little slices of time, little minute units, then we're going to get an amount, or a volume, liters. So if we take r of t times delta t, that's going to give us the amount of water flow in a small time interval, and then we're going to add those up to get the total amount of water that flowed in or out. And the analogy is that this little s here is the continuous version of the sum, r of t, delta t gets replaced by dt in our integral. And that's how we build integrals conceptually using this rate idea. What if we actually wanted to estimate this then? Well, if we want to estimate this with the left-hand rule, we would imagine a time interval. We've got 30 minutes. If we have 3 intervals that we're going to use, we divide it into breaks like that. And our integral from 0 to 30 of r of t dt is going to be approximately equal to, let's build a little table on the side here. We're using the left-hand rule, so we'll use on each interval the left, left, and left points, so 0, 10, and 20 for our times. And our rate will be 100, our rate will be 200 minus 10t. So 200, 200 minus 10 times 10 is 100, 200 minus 20 times 10 is going to be 0. Okay. Each of these time intervals is, of course, 10 minutes, and the units for the rate were in liters per minute. So this is liters per minute, this is minutes. We can approximate the total volume that's been added or subtracted. In fact, it's all added because all of these are positive, as 200 times 10 plus 100 times 10 plus 0 times 10. And these are all liters per minute times minutes. It's a very similar argument to when we did area calculations. So we'd have 2,000 plus 1,000 plus 0. So 3,000 liters is one estimate of how much water would flow into the tank in that time period. Notice it does not tell us the actual volume. So what does this say? Let's put this in a sentence form. Approximately 3,000 liters have been added to the tank over t equals 0 to t equals 30. Notice that key phrase added. it's a change. It's a net change in the volume of water. What do we need to know about the actual volume? Well, if we wanted to know V of 30, what would that equal? Well, it would be the change between t equals 0 and t equals 30. But we'd add that to the initial volume. So this change is our integral. That's how much we've added, but how much did we have to start with? That would usually be written as V of 0. What was our volume at time 0? And then from time 0 to time 30, we had all this water being added. The net change is what the integral gave us. We add the initial to the change, and we get the final. So all of these are well understood concepts, I think, for most students. The challenge is just putting it in the context of this new integration form. As a quick check here, this is a slightly, well, more exotic, I think is fair, more exotic example, but you'll see a question like it in the homework. If h of t is the height of a child in centimeters at t years, they start at 120 centimeters tall at age 10, how would you represent the amount the child grew between t equals 10 and t equals 18 years? So think about that. Take a look at the variations on the theme here, h or h prime, with or without the 120, and in a few seconds, we'll take a look at it. Okay. This question is asking for the amount the child grew. So it's asking for the net change, not the amount, but the net change in height. And that would be equal to, I guess not implies, is equal to the integral of the rate of change of height with respect to time from, in this case here, t equals 10 to 18. Again, think units. Rate of change of height would have to be in units of centimeters per year, and we would multiply that by, think of that as our delta t in years. And the only way that's going to work out is if we have the h prime. So it could be c or d. This calculation here of centimeters times years, adding those up, I don't know what those units would mean. Certainly nothing much in the context of this problem. Whereas if we add up the derivative of h, centimeters per year, multiply that by units of years with our delta t's, we will get a height back from this. Well, in fact, this is the answer. The net change in height is this. So the correct answer for how much the child grew is C. If you're tempted by D, you're right, there's something true about D. This is equal to the child's final height, not change in height, but child's actual height, or final height at age 18. Okay? And the reason is we take its change plus the initial. So there's something true about it. It involves a change, but by adding the 120, which was how tall they were at age 10, we get a slightly different value, and it has a different meaning. So just be clear in your own mind what the integral gives you and what it doesn't give you in terms of amounts versus changes.